All right, hello everyone and welcome. This week in lab, we're going to be covering the Grignard reaction, okay, which is an organometallic reaction where you take a alkyl or aryl magnesium halide, so this compound here, and you react it with a carbonyl species to generate an alcohol. So if we label the components of this, just to be thorough, so this is your alkyl or aryl. Aryl means aromatic group. Magnesium halide. In this case, the halide is bromine, okay? And you react it with a carbonyl group, so only certain carbonyl groups undergo reactions, only undergo the Grignard reaction. So those are ketones, aldehydes, and sometimes esters. Okay, if you have an ester, okay? And it reacts to form a alcohol. And we'll go into what kinds of alcohols it can form depending on whether it's a ketone, aldehyde, or ester. The Grignard reaction is said to be an organometallic reaction because it has a carbon-metal bond. So the carbon-metal bond is between this R group, so this is R1 is a carbon fragment, and magnesium is here, so that's your carbon-metal bond. It's also said to be a 1,2 addition. So 1,2 addition refers to the carbonyl carbon and the oxygen carbon. So you're adding two groups to the carbonyl. You're adding R1, so a carbon fragment, and you're adding H. So H was added here, and then R1 was added here, 1,2 addition. And finally, the Grignard reaction is characterized by the formation of a carbon-carbon bond, and that makes it extremely useful for synthetic chemistry. So if you want to build synthetic chemistry, if you want to build complex molecules, forming carbon-carbon bonds is essential. So this is a very useful reaction. Okay, now let's go over the formation of the Grignard reagent. So this Grignard reagent here, R1 MgBr, okay, Grignard reagent, needs to be formed under special conditions. And those conditions are you take an alkyl halide, so you take an alkyl or aryl halide, and you react that halide with metallic magnesium in diethyl ether, or THF, and we'll go over those solvents, and it generates this magnesium reagent. And the mechanism of how this occurs is not thoroughly understood, but some might say that this magnesium sort of inserts itself in between the carbon-halogen bond here. Okay, so the characteristics of Grignard reagents. So if you look at this Grignard reagent here, it is an organometallic species. And this magnesium here is very electropositive. So the electronegativity is very low compared to carbon. So this carbon here will have a delta minus. So overall, there's going to be a dipole towards the carbon here because the magnesium is not withdrawing electron density. So you can also think of a Grignard reagent sort of as the carbanion, so sort of as a carbon with a negative charge with a magnesium bromide or magnesium halide counterion. So that kind of explains the reactivity of it, in that this is now a good nucleophile. Carbon nucleophile. So one of the characteristics of the Grignard reagent is that it's a good nucleophile. And of course, the electrophile in a Grignard is the carbonyl species, but it's also a very good base. And this arises to certain issues, so-called incompatible groups. So some functional groups that are incompatible with Grignard reagents are alcohols, water, some amines. If the amine has a nitrogen, it could deprotonate it, and also, obviously, carboxylic acids. Those react with bases. So if you have a R magnesium halide, and you mix it with an incompatible group, say an alcohol, and these groups are protic groups. So they have a acidic hydrogen. The base is strong enough, or this group is strong enough to attack the hydrogen and deprotonate it. Okay, and in doing so, you form an RH bond and the conjugate base of whatever this group is, in this case an alkoxide, negative charge. So this R group is basically, you've destroyed your Grignard reagent. it will no longer react with electrophiles because it has its negative charge been canceled. Okay, so the role of the diethyl ether and the THF is to stabilize the complex. So as I mentioned before, this is an interesting organometallic complex, and in the magnesium, because it has a partial positive charge, it's attracted to the oxygen atoms in these structures. So diethyl ether and THF are both ethers, and the oxygen atoms will sort of stabilize the magnesium atom because they have partial negative charges. So it sort of keeps the magnesium happy under these conditions. Okay, let's talk about the certain products you can generate from a Grignard reaction. So on the left we have the same reagent, Grignard reagent, R1 is a carbon fragment, and then we have different electrophiles we're going to react them with. The first one is an aldehyde. So if you have an aldehyde functional group, you're going to generate a secondary alcohol as the product. So you can see this is a secondary alcohol because the carbon the OH is connected to carbon fragments. So the H here makes it a secondary alcohol. If you react magnesium bromide with a ketone, where it has two carbon groups here, so this is a ketone, you're going to get a tertiary alcohol as the product. Okay. If you react it with an ester, this is an interesting circumstance. If you react a Grignard reagent with an ester, the first step is an addition, as we'll see. The electrons go up, forms a tetrahedral intermediate, they come down, but they kick off this OR group. Okay, so we've gotten rid of this OR group, and now we've attached the R1 group. But the problem is now we have a ketone, and ketones still undergo Grignard reactions. So what happens is a second addition where R1 is added twice, and we still end up with a tertiary alcohol. So there's two R1 groups now. In this case, example, you take the Grignard reagent and you react it with carbon dioxide, CO2, and you generate a carboxylic acid. Okay, so this would be attacking the carbon here, kick those electrons up, and then when you work up the reaction, you'll protonate this O and then form the carboxylic acid. Finally, here's a little example where we're trying to figure out, well, what's the product of this reaction? And sort of a trick question, because you might expect that it would add to the ketone here. So this would attack the ketone and form a tertiary alcohol. But as you can see, this substrate actually has a protic portion. It has an OH group, and that OH group is very acidic compared to this Grignard reagent. So the faster reaction will be that it takes the hydrogen instead of reacting with the ketone. So now you're going to get methane. So this was methyl magnesium bromide. Now you get methane, and then you have the conjugate base of this substrate. So something to keep in mind. If there's an incompatible group on the Grignard reagent or on the electrophile that you're using, an acid-base reaction will occur and the Grignard will fail. So this is where protection comes into case, where you have to protect these reactive sites in a Grignard reaction. Finally, let's take a look at the reaction we're doing in this specific lab. In this lab, we're taking bromobenzene. This is our aryl halide. We're reacting it with magnesium and diethyl ether. So that will form our Grignard reagent here. This Grignard reagent, we're going to react with a ketone electrophile, benzophenone. So this group will add to this carbon, and we're going to form the product triphenylmethanol. So as you can see, this phenyl group came from the bromobenzene, and then these two phenyl groups came from the benzophenone. And as we expect with a ketone, we're going to get a tertiary alcohol as the product. Briefly, the mechanism is fairly straightforward for this reaction. So for this reaction, you take bromobenzene, and we're just going to assume it's already as the Grignard reagent, so magnesium bromide. Okay, and then you can imagine having benzophenone here. And simply, this bond swings out, acts as a good nucleophile, and attacks the carbonyl group here. And now it's going to form our triphenylmethanol. It's going to look very similar, but it's not going to be entirely there. Okay, so here's our adduct, our addition product. it's going to have a negative charge here. And that negative charge needs to be neutralized. By the way, the counter ion is still the magnesium bromide. So law of conservation of charge, we're still neutral here. Then you simply add an acid in the workup. So when you hear of an acidic workup, this is what it refers to, is you're protonating the alkoxide species. So that group will become protonated. Oops. Okay, and there's your alcohol product. So this is essential, this step when you work it up. You need to protonate this site in order for you to isolate this product. There is a bit of a side reaction going on here, an unproductive side reaction in this specific experiment. Say you have some magnesium bromide. Well, magnesium bromide is a good nucleophile, and we are working with an excess of bromobenzene, so there's going to be a little bit of unreacted bromobenzene. So what can happen is actually sort of like a substitution reaction where it will attack this carbon because it has a good leaving group, and it will eventually form biphenyl as a side product. The mechanism is not an SN2, but you can sort of think of it as an SN2 reaction. So this carbon is forming a bond to this carbon, and you generate biphenyl as a side product. And then we're going to employ a technique, a new technique, sort of like a new technique called tertiaration to remove the biphenyl. Okay, see you in the lab. Okay, so we have our apparatus here. So this is probably the most complex apparatus we've ever had. And as I stated, this is the most challenging reaction to perform in this sophomore organic chemistry class, simply because it's very sensitive to water. That's the issue we're dealing with here. Grignard reagents are extraordinarily sensitive to water. So much so that the glassware itself can destroy your reagent. You might not think of it, like you look at a flask, it's dry, but glassware, because of its silanol groups, are very polar. So even on dry glassware, there's a very thin, very perhaps atomically thin layer of water that's adhered to the inner surfaces, and in fact the outside surfaces of the glass, and that water will react with your Grignard reagent. So before we can even make the Grignard reagent, we have to heat the apparatus. Now, this could be done by heating the glassware overnight in an oven, but that's not possible in this case. So what we've elected to do is flame dry the apparatus. So what we're going to do is we have a Bunsen burner here, and we're going to ignite it and heat the glassware very carefully. And at the same time, we're going to pull a vacuum so that will suck all the water vapor out. Okay. And when you flame dry, you got to be careful, especially when you're doing it under vacuum. You don't want to linger in any one spot for an extended period of time. I've also checked the glassware for cracks since we're putting it under vacuum. There are no cracks. Sometimes if you have a crack in your flask, it could lead to an implosion, but here we're good. So we have our round bottom flask. We have a Claisen head to have two features, two different pieces on here. We have a sep funnel, which we're using as an addition funnel, and then we have a condenser. Okay, so let's start the gas. Okay, we'll just make sure to keep this tube out of the way. Okay, so the Bunsen burner is lit. We'll adjust it so we have a blue flame, so you can sort of see the flame here. And I'm going to turn on the vacuum and then heat the apparatus, and you'll be able to see some of the water vapor evaporate or vaporize and be sucked out of the apparatus. You'll also see some water vapor on the outside of the glass, so you can see them. Okay, so we heated it, pulled it under vacuum. We'll take the vacuum line off here, and then we'll replace this with a stopper because we don't want any water vapor to get back inside here. So just take that out and put a little stopper in there. Okay, so now the apparatus is hot, so the glass is still very warm. So we're going to let this cool, and then we'll start making the Grignard reagent. Okay, so we've allowed our apparatus to cool, and now it's sitting over a hot plate. So this hot plate we're going to use a little bit for heat, but mostly for the stirring. Okay, we're going to add our solvent now. Oh, I should have mentioned, the magnesium turnings was already in there when we flame dried it. So that also helps to sort of dry the magnesium. So make sure there's no water adhering to the magnesium on there too. So our magnesium is in there. We just need to add our solvent and our halide. So solvent first. We're using diethyl ether. So diethyl ether is inert. It's not protic, so it's not going to react. But it's also anhydrous. Anhydrous is important because you need it to be free of water. Anhydrous means without water. And to add to this flask, we're going to add 10 mils here, and then we're going to add 10 mils to the sep funnel. In fact, I think I'll just add both of them through the sep funnel. So we're going to add a 10 mil portion first, and speed here matters more than precision. So we want to be fast because the ether will absorb water from the air. So we're going to try to get around 10 mils here. And ether is very flammable as well. Has a very low boiling point, which also makes it challenging to work with. It likes to vaporize. Okay, so there's about 10 mils. Quickly stopper the container, and then we'll add the ether. You can see it's already, the apparatus is just warm enough, it's still warm, that it's actually vaporizing some of the ether. So there we go. Okay, so we've added about 10 mils of ether in there, so you can see the vapor pressure is so high that it's actually causing the stopper to bounce. Anyway, so now we're going to close it. So we've added around 10 mils here. Now we're going to put 20 mils in here to it. If you look closely, you can even see the refractive index of it, see the vapors kind of flying out. Okay, and we'll stopper it. Okay, so also we're keeping the apparatus stoppered for now. So typically you never want to heat or work with a sealed reactor just in case something explodes. But here we're concerned about keeping water out, water vapor in the air out. And you'll notice we have a condenser here. So this condenser is going to help keep the vapor, the ether, from leaving, though it's not very effective here in Hawaii because the tap water here is very warm and diethyl ether evaporates at just barely above room temperature. So it's going to do something, but we're still going to lose some ether. Okay, now we're going to add our halide. So here's our bromobenzene. Okay, it's about 3.5 mils. We're going to add about half of it to the flask here and about half of it to our sep funnel. Okay, so I'll grab a pipette. And you can sort of eyeball this. So I'm going to add about half to this sep funnel here. Okay, and the remainder I will add directly to the solvent here. Okay, so we have our bromobenzene and ether solution in the sep funnel, and then we have bromobenzene and ether in the magnesium. And with any luck, they should start reacting. So we'll add the stir bar. The stir bar helps agitate the magnesium, helps it to react. And this is perhaps the hardest part of the Grignard, to get the reaction going. Many chemists struggle to get this reaction going. It's pretty finicky sometimes. A good indicator that it's occurring is that you'll see the solution turn sort of turbid, sort of light gray, perhaps a little light brown, and it'll start to fizz and in fact reflux in here. Okay, so I'll let it go for a few minutes and we'll see, hopefully it starts. And then once it starts, the goal is to sustain the reaction by adding bromobenzene periodically. We don't add it all at once just in case there's a runaway reaction and it generates too much heat and it all boils out. Okay, so hopefully this starts. We've waited a few minutes. It looks like our Grignard is not going as planned. It's not initiating. So we're going to employ one of the tricks. There are numerous tricks people do to initiate Grignard formation, and the one we're going to use is we're going to add a crystal of iodine. So The iodine will help sort of etch the surface of magnesium, of the magnesium metal, increasing the surface area so it begins to react. So I'll take a crystal of iodine and then basically place it in here. And it's going to color the solution a little bit, but that's okay. So we'll take just one crystal of iodine. So that should be enough here. So I don't know if you can see that, but it's very nice looking. Iodine is a pretty element. But when it goes into solution, it forms kind of a dirty brown, so it's not that nice to look at. Okay, so hopefully this will initiate our Grignard for us. So I'll take this Claisen head off and add the crystal quickly. So there we go. So you can see it immediately colored the solution. Okay, so hopefully this helps initiate the reaction. Alright, so we've added our iodine. It's stirred for a few minutes, but it's still being pretty stubborn, which can be typical. So the perhaps most foolproof way is to simply take a stir rod and jab at the magnesium, crush it, expose new surface of the magnesium to help it go. So that's what we'll do. The risk here, though, is punching out the bottom of the flask. It has happened where students kind of jam it too hard and it cracks the flask or breaks the stir bar or the glass stir rod, so you do have to be a little careful. So, oops, sorry, wrong one. Keep that clamped. We'll take this out. Okay, and it's as crude as you would expect. You simply just take the stir bar and you start jabbing at it. Okay, seems like we might be getting something here. There you go, you can see it lightening in color. Nice, okay. There we go. I think we've started here. Yep, so you can see the solution is becoming slightly turbid. Okay, so this should be sufficient here. The magnesium should begin to react. And what we're going to do is we want to sustain this, bring it up to a reflux. Not really a real reflux, I mean ether boils at such a low temperature, so we just have to heat it so mildly. We'll set the hot plate to low, and just the hot air is enough to heat the flask. So the flask is not touching the hot plate. A little bit of a gap here. But that little bit of heat generated should be enough to keep this reacting. So you can even see it beginning to fizz here. So that's what the initiation looks like. You can see it fizzing. Okay, and then now we're just going to drip in the bromobenzene slowly. Oh, see. It's warm enough to kind of push the stopper out here. Okay, and what we'll do is we'll undo this stopper here gently. You can sort of, in fact, you can probably inert it. So this will not form a seal here. So there's no overpressure in the system, but it will sort of prevent too much air from flowing back in. So we're just going to keep this going. It's going to take maybe 10 or 15 minutes. At the end of it, most of the magnesium will be consumed. There will be a few pieces of magnesium left over, but for the most part it will stop fizzing and most of the magnesium will be gone. You can see the condenser now recondensing some of the ether. So you might even want to taper the drip rate here. If you overheat it, so say you add too much bromobenzene or you heat it too much with the hot plate, the ether might make its way out at excessive rates, so you'll lose all your solvent. You don't want to do that. So this is not a very high efficiency condenser. So okay, so our Grignard reagent has been forming for about 15 minutes or so, and there's still a little bit of magnesium that's unreacted. So that's to be expected though, because the magnesium is in excess. So now that's the formation of the Grignard reagent. In this flask is the phenyl magnesium bromide. Okay, so basically step one of this experiment. In this vial we have benzophenone dissolved in diethyl ether. So benzophenone is the electrophile which will react with our Grignard reagent, and we'll add the benzophenone to our sep funnel here. Okay, and make sure the stopcock's closed. So. Okay, so we've charged it into our sep funnel, and now we're going to add it. So when we add it, oh, you can even see some of the benzophenone residue here on the vial. Anyway, so we have our benzophenone in here, and we're going to react it with our Grignard reagent. And now this reaction is very fast, so it occurs basically spontaneously, and you'll see a rapid color change. It's very nice to watch. And when we add it, we're going to be careful to add it slowly, because the addition is exothermic, and it's so exothermic, in fact, that a lot of ether escapes out the top. So we're going to try to add it slowly. So now, in fact, why don't I turn the sep funnel this way so I can turn this. So watch closely, because there's a cool color change that occurs. Okay, going to add a little bit of ether to the sep funnel to kind of rinse out the residual benzophenone. Nice. So this is typical for this reaction. Eventually there's enough product, the solid is the product, that it precipitates from the mixture. And now we have a nice solid in here. So, in fact, so much so that the stir bar is getting a little clogged. So it went from looking like fruit punch, now looks like Pepto-Bismol. There we go. So I'm having to turn the stirring very vigorously to get everything integrated. Okay, so I think what I'll do is I'll kind of scrape down the sides with a stir rod. A little challenging. Make sure everything is integrated. There we go. There's no pockets of unreacted benzophenone. Okay, nice. So at this point, our Grignard reagent has been pretty much fully consumed, and it's reacted with the benzophenone to form the triphenyl methoxide adduct. So the adduct consists of the deprotonated triphenyl methanol and the magnesium bromide cation, and that is very ionic, so it's not soluble in diethyl ether, which is why it's precipitated out. Okay, so now what we can do is we can get some hydrochloric acid. We'll place the hydrochloric acid in the sep funnel, and then we'll drip it into the reaction. So here we don't really care about getting air or water in the mixture, since the Grignard is complete. So in fact we can remove some stoppers here. Okay, so we'll get the hydrochloric acid, and then we'll begin adding it. Okay, so we have some 3 molar hydrochloric acid here. We're going to add it to our sep funnel. Okay, and we're going to start dripping it in. And this will destroy the adduct, so it will protonate the alcohol and keep the magnesium salts in solution, and dissolve any residual magnesium that wasn't consumed in the first step. So we'll begin adding it slowly. We found that if you go kind of slowly in the addition here, it dissolves better. And when this occurs, it will probably get rid of this pink color, and it will turn into a sort of light color biphasic system. So there'll be an aqueous layer, so you can already see it's bubbling vigorously. There'll be an aqueous layer at the bottom and a ether layer at the top, the organic layer. And we're trying not to overwhelm the condenser here, so we're kind of, you can see the ether is climbing very rapidly because this is the most exothermic step out of all the steps. Alright, so as you can see, we've added all the hydrochloric acid from the step funnel, and now we have a very nice biphasic mixture. So the top is the ether layer, that's a little bit yellow. That can be due to two things. One of them is the triphenyl cation. So in acidic solutions, the OH might leave as water, and then you get a carbocation, which is delocalized among the three phenyl rings. So that might give you the yellow color. But the other yellow color that it could come from is the biphenyl. So the biphenyl is slightly yellow, so that could be it. And you'll notice there's a little bit of fizzing at the interface, and that's from the magnesium being dissolved by the HCl. So we'll let this stir for a few more minutes, and then we'll separate the layers. Okay, so we have our mixture here. We've disassembled the apparatus. We have our biphasic mixture. So it's a little hard to tell, but in the lower phase is water, and then the upper phase is ether. Okay, so we're going to take it and pour it into this subfunnel here to separate the layers. Okay, I use a little ether to rinse out the flask. Okay, so lower layer is the water, upper layer is the ether. We're going to remove the lower layer. So the lower layer contains the excess hydrochloric acid and the magnesium salts. Okay, and then to clean the ether layer, we're going to add some brine. So this will wash out residual HCl, as well as pull out any water that's stuck in the ether layer. And as with previous labs, we shake and vent. So, and here you really have to be careful to vent frequently, because ether, as we stated, has a very high vapor pressure and likes to boil away. Okay, so no emulsions here, nice clean separation. So we can just drain away our brine. Okay, so now we have our product. Our triphenylmethanol should be mostly in the ether here. Okay, and then we're going to add that to a Erlenmeyer flask to dry with sodium sulfate. Okay, so here's our ether layer. We're going to add the sodium sulfate to absorb excess water. Yeah, so you can see the sodium sulfate is clumping to large aggregates, so we'll add a little bit more. Yep, so that looks about dry enough there. So we'll let this sit for a few minutes, and then we'll put it into this beaker and get rid of the ether. Okay, so we have our ether layer, which has been drying. We're going to decant it carefully, as carefully as we can, into this beaker here, where we can evaporate the ether. So I'm going to do my best not to filter it. You could filter it, but we're short on time, so we're going to try to transfer as much of it as possible without getting any solid. With sodium sulfate, this is not too difficult, but if you use a finer, more powdery drying agent like magnesium sulfate, this can be challenging. The triphenylmethanol is pretty insoluble, and even in organic solvents. So if you see the Erlenmeyer looks a little frosted, that's because the ether is evaporating and leaving behind a coating of the triphenylmethanol. So I have some ether here. We'll use it to rinse and try to transfer as much as possible the triphenylmethanol. Yeah, see, already you can see that evaporating again. And okay, so this yellow color, as I said, is probably from some residual biphenyl, the side product, which is colored yellow. To get rid of it, we're going to use a technique called tertiaration. Tertiaration is a sort of like just washing a solid normally with a solvent that does not dissolve your target compound, but does dissolve the impurity. So it's kind of like recrystallization. One way to do it is to take the crude solid and wash it with the solvent that will get rid of the impurity, in this case hexane. But the other technique is you can simply make a mixture of the two solvents and then start to boil it down. So we're going to add about 10 mils of hexane here. So I'll just pour some out. So when I add the hexane to the beaker, the solution should remain homogeneous. I'll add around 10 mils. It should remain homogeneous, so everything should remain in solution when I first add it here. So I can add the hexane. Yeah, so homogeneous. And hexane and diethyl ether are miscible, so they mix. So as we boil this away, we're going to put this on a hot plate. As this boils away, the concentration of ether will decrease and the concentration of hexane will increase. So as the concentration of ether goes down, the triphenylmethanol will precipitate, which is our target, but the biphenyl should remain dissolved in hexane because biphenyl likes to dissolve in hexane. So we'll take a hot plate here. Okay, so here's our hot plate. Turn it around about half and we'll place it on here. We're just going to be pretty careful when we do this because boiling off ether can be a little dangerous, so we'll be careful. I'm going to stir it periodically to make sure it doesn't bump. In fact, what I'll do is I'll take it off, I'll let it cool a little bit and add a boiling chip so it boils nicely. Okay, so we added a boiling chip, so now it's going to boil smoothly. And all we have to do is wait. So we're going to wait until we boil off enough solvent so that we have about 10 to 15 mils remaining in the beaker. And at that point, there should be a large quantity of triphenylmethanol precipitate, so most of the ether is gone and it's primarily hexane. In which case we can put it in an ice bath, make sure all the triphenylmethanol is solid, and then filter away the hexane. And the hexane should contain the biphenyl impurity. Okay, so here we have our mixture. We've removed it from the hot plate. It stopped the boiling. So the residual solvent in here is hexane, and you can see it's yellow, but our product is nice and white. So what we're going to do now is, I guess the first thing I'll do is I'll kind of try to break up this solid just to make sure it's suspended. So there we go. So hexane, if you wanted to be really pedantic about it, you could say that hexane is the anti-solvent of triphenylmethanol, whereas ether is the solvent. So as the concentration of the anti-solvent increased, our triphenylmethanol began to precipitate. but our biphenyl is soluble in both. So that's what we get. So we're going to place this in an ice bath to make sure we get all the triphenyl methanol as possible, and then we'll filter away the hexane. So we have an ice bath in here. Keep it cool. Okay. Okay, so we have our mixture here, which has been chilling in an ice bath, so nice solid. So I'll take a spatula. Here it is. We'll sort of agitate it, and then we're going to filter it on this filter here. So in fact, first, why don't we wet the filter with some hexane. So I have some cold hexane here that we'll use. So now we can take our solid and filter it. So there. So we'll use the hexane in here to rinse out the beaker. Okay, then we can add the remainder of the hexane. And then this will serve to wash out any residual biphenyl. Okay, as you can see, the product is a nice white powder, so that's a good indication that we're fairly pure here. And then the filtrate here, which is hexane, should have the biphenyl impurity. Okay, so we'll get this onto a filter paper and then transfer it to a scintillation vial. Okay, looks good. Here's our filter paper. Try to scrape off anything there. There's not much here though. Okay, there we go. Okay, so we have our solid here. Okay, so our product, we've dried it in a desiccator to get rid of any water or hexane under vacuum. So as you can see, it's nice and white, not very much yellow, indicating that it's pretty pure, but we'll also put it in the mass spec to check that it's pure. And the mass on it is about 4.82 grams. Okay, so you can use that to calculate your percent yields. So 4.82 grams. Okay, we're here at the LCMS. We have a LCMS sample prepped here. So we put a milligram or a few milligrams of our product in here with acetonitrile. We'll place it into the tray here, and then we'll run the LCMS and we'll see if our product is there. Okay, so our sample finished, and we're going to go to the data analysis, figure out what's going on here. So this is our sample. Looks like this is the UV peak here. This measures the absorption of UV light, of UV light. And then here's our positive mass spec mode. So the mass spec is monitoring for positive ions, which is what we're concerned with. So this peak here, we'll take a look at. So here we have an array of peaks. And if you'll think about it, so I'm not sure what these peaks are here at around 350 to 380. The product mass, molar mass, is 260 grams per mole. The problem is we don't see 260 here. So you might think, oh, well, our product's not very pure. We don't even see our target mass here. But if you look at this peak here, this is 243. And 243 corresponds to the molecular ion minus 17. So if you add 17 to that, you'll get 260, which is the mass of the product. And the reason being is because in the mobile phase, there's some acid, and when the OH of the trityl alcohol is protonated, it leaves. And when it leaves OH. So subtract the mass of one OH group, which is 17, and you get this peak right here. So this is the trityl cation you're seeing here, trityl or triphenyl cation. I'm not sure what these peaks are, 350 or 384. They could be adducts, or they could be impurities. They're not benzophenone, because benzophenone has a mass of 182. So we don't see any benzophenone in here. So if you have any idea what these ions are, please let us know. We're very interested to see what you think.